and also the half adder. Okay. Since we already learned the circuit of full adder and half adder, we can just calculate all the possible path delay. I'm sharing you my whiteboard here. This is your half adder. And this is your full adder. In your half adder, there are two paths, which is from A or from B to S, and from A or from B to C. Let's just take A to S and A to C. So A to S is, okay, let's say the XOR is 2 tau. XOR is 2 tau, and other gates is tau. So from A to S is 2 tau, the delay is 2 tau, and from A to C, that is tau. Same goes if you choose B instead. B to S is 2 tau, B to C is tau. Okay. All right, in your full adder, okay, as I explained to you before, we have 4 possible paths, which is from A to S, okay, from A to S, the green line, the green path, from A to C, okay, the red path, from C, which is the previous carry, the lower order carry, from C, okay, from carry to S, and from carry to the higher order carry, from carry to carry, right? So from A, from input A to S, it will take you 4 tau because we're going through 2 XOR, right? From A to S is 4 tau. From A to C is 4 tau because we go through 1 XOR and then another 2 gates. And then from C to C is just 2 tau. And from C to S is 2 tau. Okay, so you can just remember this. You can just remember this formula. There are 4 path delays in full adder, which is from A to C, A to S, C to C, and C to S. And if it starts from A, it will take 4 tau. If it starts from C, it will take 2 tau. And for half adder, there is 2, which is from A to S and from A to C. Okay. From input to S and from input to carry. If from input to sum to S, that is 2 tau. From input A to carry, that is tau. Okay. Remembering this make it easier for you. Okay. But this is in the case of one XOR is 2 tau and other gate is tau. Okay. In the questions, the condition might be different, where one XOR could probably 1 XOR is equal to 3 tau, for example. So you also need to remember what is inside the path. Okay. From A to C, there's 1 XOR and 2 other gates. From A to S, so that's 2 XOR, and so on. Right. So let's do the analysis on how can we say the critical path delay or the longest path delay is 14 tau. This is the CPD, path delay. All right. So first, we have to check all the paths. So this is a half adder. In half adder, we have a path from input to carry, and then from input to sum. Now, from input to carry, using half adder, sorry, input to carry, that is tau. So we just write 1. We exclude the tau, just write the number, because this is 1 tau, right? So this is tau. And then from input to sum, this is 2. Okay. And then we have another here from input to carry and from input to sum. But the input is up here. So to go to this carry, we are bringing along this delay. So from this input to this carry, that is 2 plus 1, which is 3. And to this sum, okay, it is 4. This 2 here, it's another 2 here, that is 4. Right? So that is for half adder. Now we're going to into the full adder. Right? So in full adder, we're going to see from input to carry, and then from input to sum. And then we're also going to see from carry to carry, and then from carry to sum. Right? Same goes here. Full adder, there's 4 paths that we have to check. From here, from input to carry, A to C, or this one, A to C is 4, and C to C is 2. Here from A to S, that is 4. And from C to S, that is 2. Now we only want to find the CPD, which is the critical path delay. So we eliminate the delay that is not the longest. We only took the longest delay. So we eliminate 2 here because the longest delay will be 4 here and 4 here. Okay, which is from A to C and A to S. It's 4. Okay? And we're going to repeat that until we reach here. Right? So for this,
Doctor,
yes.
for the blue line, suppose it become 3 because we already have 1 tau from half adder.
Yes, it's 3. Thank you. Now for this one, from C to S is C to S. C to S is 2. 2 plus 3 is 5. Okay. Then this is 5. Then this is 4 plus 4 is 8. Then 4 plus 4 takes 8. And we're taking the 8. Okay. 8. Okay. And then we're still going to do the same thing. Right. Here we have 4 plus 2, which is 6 for the blue one, and then 4 plus 2, 6, and then 8 plus 2, 10, 8 plus 2, and then for the red line, red path, okay, it's 4, 4, okay. This one, we eliminate the 6. Sorry, we eliminate the 4, we're taking the 6. This is not 10 yet. I don't know. Four, four. Then 6 plus 4 is 10. Same thing. 6 plus 4 is 10. It's the same. Okay? And then, right, let me know if I'm wrong. Okay. And have both on this.
Is it 6 or 5?
Here,
Is that 6 or 5?
we have
1 plus
4
2
here.
plus 2. Oh, I know. Oh,
It's
4
from
plus
here.
2.
4
Oh, yeah.
plus 2. Okay.
Thank you, doctor.
No problem. All right. And then we will do the same here. Okay. This is full edit. So, this is 4. Blue is 6 plus 2, 8. 6 plus 2, 8. Okay. And then the red one is, we eliminate 4 because 8 is more critical. And then 8 plus 4, 12. So 8 plus 4, 12, same. And then the blue one, 10 plus 2, 12. 10 plus 2, 12. Same thing. And then for half adder, it's either, okay, we can go here or we can go here. It's the same, because this is the C. This is supposed to be the C. This is the S, right? So from input to C, this input to C, this input to C, this input to S, and this input. There's 2 different input. So should I make it different color? From this input to S, from this sorry, to C, from this input to S, and then from this input to C and this input to S. Okay, if it coming from this input, it will be 10 somewhere here, and then if we go from here, that's 12 plus 2, that's 14, right? 14, and here is 10. Okay. Red. This is 8 plus 2, 10, and 12 plus 2, 14. So the the delay is 14. Okay? Delay is 14. And then, if the question says, calculate the delay. Calculate delay, or maybe it says propagation delay, which is the symbol is TP or TPD. Sometimes time of propagation delay, or you say calculate the CPD, calculate the critical path delay. So the delay is 14. And this is how we calculate. And then the question might ask you, trace the path, trace the CPD. So to trace the CPD, let's use green and this one. You can see green here. So the path is, there are multiple paths here. So we are not taking any of these paths, because we eliminate this path here, already eliminated, and this path, can you see my mouse? I'm not sure if you can see my mouse.
No.
No, okay, that's great for telling me. Thanks for telling me.
Yes, I can. Now I can.
Yes, now you can. All right. Okay. We eliminate this path. When we eliminate the tree here, we eliminate this path. So this is not going to be in the path. This path, okay, and here this straight path. So this is not the path. And this path with 3 tau here is eliminated when we eliminate the 3, the 5 here. So we eliminate 3. Okay. The 8 here is coming from 4 plus 4 here, right? So the path will be, hope you can see the green. Can you see the green?
Yes.
Yeah, it's hard to see, but I hope you can see it. Okay, it will be this path, okay, or this path, or this path. Okay. So there are 3 paths. So if you were asked to trace CPD, then you have 3 paths, okay, to trace.
Excuse me, doctor.
Hmm?
Should we draw the 3 paths in the test, or just one is enough?
I suggest you draw all 3, okay? Because I'm also not sure how the question will be. Sometimes it's not clear. Well, it's good to just draw all 3. Sometimes when I see the scheme, the marking scheme, it say 1 is enough. But sometimes maybe you should check the number of mark, or just ask me in the test. Okay.
Okay,
But
thank you, doctor.
if you ask me during the test, I would just say draw all 3. That will be my answer, right? Not
Okay,
draw all
okay.
3. I mean draw all paths. All right. Okay. So that is how we calculate the CPD and trace the path. So back to this. So now
Doctor, I have a question.
Yeah, questions. Yes. Questions? Okay. Right. Come back again when you have the questions. Shall we continue?
I lost my connection. Sorry.
Oh, okay. You're okay now?
Yeah, okay.
Okay, you want to ask questions? Why is it?
Why we didn't use RCA with 10 tau?
Why we didn't use RCA? Because it's
With
already in
10
different
tau delay.
connection now. How to calculate the RCA delay formula?
No, we already know RCA delay is 10 tau. Why we didn't use it like 10,000 we calculate for CBA?
Because it's now a different path. The S is now connected to another path. Okay, so the possible path is now different. So you have to calculate. You have to calculate each possible path, each delay for possible path. Okay. You can only use the RCA equal to RCA 10 tau is only 4 bit. 4 bit RCA is 10 tau. Okay. N bit RCA is, remember the formula?
2n plus 3.
2n plus
3. N is equal to the block or RCA block.
2n plus
3.
3? Is it?
Yeah.
Check again. Okay, check again. I think it's 2. I think it's 2n plus 2. Because 4 bit RCA, you will get 8 plus 2, right? That's 10. Yanas,
No, it's plus 3.
why is it plus 3? If it's plus 3, then 4 bit RCA, you will not get 10.
N plus 2 for RCA. 2n plus 3 is for CLA.
Dalam Sahih
2n
Muslim
plus 2
disebutkan
for RCA.
siapa yang meringankan satu kesulitan
2n
Okay.
plus 3 is for CLA, Anas.
2n plus 3 is for CLA.
CLA.
Anas. Hope it helps. Thank you, Sam. Sam Wong. Right. So we have different paths here. Now we have different paths, different connection. Okay. RCA, the connection ends at the S here. Ends here. Like this, it ends here. Okay. But this circuit S has connected to another circuit. So we have to find the new path. Find the new path for it, and then find the delay of the path. Right? It's not the same path as the normal RCA, because we have cascaded and design it like this. Okay, so I hope you can find the delay here. Okay. The delay for this using the same formula. Okay. Remember, the FA has 4 paths, which is from A to S, which is 4 tau. Okay. A to C, which is also 4 tau. If it starts with A, then it will be 4 tau. And then C to S is 2 tau. And then C to C, which is the higher order C, that is also 2 tau. And for half adder, we have A to S, that is 2 tau, going through 1 XOR. And then C to S. Sorry, wrong, my bad. Let me erase that. Erase that from your memory. It's A to C. So, okay. Remember this, then you can do this. Same goes, I don't remember which one. Same goes as this one. We can use the same method. We can use the same method to determine the CPD. Question asks you to determine the critical path delay, critical path and the critical path delay. So instead of finding the path one by one, then you write down the path like A, D, H, M, Y, B, E, F, H, M, Y, B, F, H, M, Y, and many more, and then find the delay one by one. You can just find the delay. Just find the delay after each gate, and then eliminate choose the longest delay. Choose the longest delay until you reach the end of the circuit. Yeah,
Dia tengah duk ajak ke apa sangat?
it is easier
Oh ya.
to
Kalau
find
ada
the delay
break cakap.
by tracing it instead of listening all the possible paths and calculate the delay. Right? Understand? Okay. Let's get back to this if we have time later. Now, okay. Subtract together and then condition codes. So we have 4 condition codes. Right, this one. So this is the code where we have using adder, and subtractor. We can do both, adder and subtractor, and C in here is connected with XOR, so we can find the relationship.
Ni kena request lah, bukan dia join tu ke? Cuba aku masuk.
Okay, so we know that using adder, so this is adder, full adder, full adder, full adder, full adder. Using adder circuit to subtract, the formula is A plus B flipped plus 1, right? So this B must be flipped to subtract, and the LSB is added with 1. So it's like if you have A0, A0, A1, A2, A3 plus B3, B2, B1, B0, and then plus 1 here. So this will be done in each of the full adder. So this full adder will calculate A0 plus B0 plus 1. This B is flipped. This is A1 plus B1 flip, A2 plus B2 flip, A3 plus B3 flip. This is how we subtract. And here we use C0 as the third input, which is C0 must be 1. C0 must be 1 to perform the subtraction. Because the third input of the full adder here must be 1, right? Okay, and in order to make the C01, the condition is these two conditions. If sub is 0 and C in is 1, or if sub is 1 and C in is 0, then we can have the third input as 1 here, the C0 equal to 1. Okay, but we also have to see the B0 and C is connected with X. So B0 and B0, 1, 1, 1, 1, 0. So we want if you want to do subtraction, if you want to perform a subtraction, this B must be flipped. This B must be flipped. So the XOR must flip the B. So which one is flipping the B? And this one. When sub. Okay. Okay, when sub is 1, it will flip the B. But when sub when but so to perform a subtraction, the condition is sub must be equal to 1 and the C in must be equal to 0. Okay. If C in is equal to 1, okay, even though the sub is 1, it will not perform the subtraction because the C0 will be 0. And if the C in is 1 when sub is 0, okay, although the C0 is 1, it will not perform the subtraction because in that case, the B
No
is not
CO.
flipped.
Nothing.
Oh, okay, in that case, B is not flipped. Okay, let me repeat again. Okay, in case C in is 1, C0 is then C in is 1, sub is a 0. Okay, even though the C0 is 1, it will not perform the subtraction because the B is not flipped. So the only possible condition to make the B flip is when sub is 1 and C in is 0. So that is for this circuit. So the other condition could be added and could be another arithmetic equation. General arithmetic equation. Right? Okay, done that part. That was the confusion last time. Any question here? If not, I would like to proceed. So, deriving the other relations. So sometimes when we compare two inputs, let's say we want to compare input A and B, we use subtraction. We use subtraction as comparator. We use subtraction as comparator. Let's say we want to check if A and B is equal. So we will perform A minus B to check if A is equal to B. Condition, right? We want to check A. If A equal to B, we subtract B from A. So A minus B. So if the answer is 0, okay, if the answer is 0, Z flat is set to 1. the Z flag is 1. So instead of checking the answer, which is equal to probably number of bits, okay, if this is a 4-bit calculation, we have 4 bits, we only have to check which is the Z bit. Okay? So it reduced the checking time. Right? If we want to check this condition, we can check the Z flag. And then if we want to check if A not equal to B, okay, you always use this not that you have experience writing this kind of conditions in C programming or other programming, right? So when the hardware want to check this relation, okay, whether A is not equal to B, we'll subtract B from A minus B. Okay? And if the answer is 0, Z flag is 1, but if the answer is not 0, Z flag is 0. So the computer has the Z is 0 or not. Okay, if the Z is 0, then we know that it is not equal. Okay, when the Z is 1, we know that A and B is equal. Right. And then we want to check if A is less than B. If A is less than B, so if A minus B is negative, means it's less or not? Means it's less, eh? Let's say A is 3, B is 5, A minus B will be negative, minus 2. So if A minus B is negative, then we know that A is less than B. And if it's negative, C flag, where is it? Let me see. If it's negative or unsigned, for unsigned, we will check the C, which is the what is C? Carry. And then for flag, we will check negative flag and the overflow. If A minus B is negative, the carry will be 0. Is it? Right? Is that correct, everyone? Carry is 0.
Baru.
Tak faham saya. Udah baru bangun ni.
Uish, kau masuk ke Aziz?
Tadi aku call korang, dia aku bawa masuk tu.
Oh iya tu. Aku tengok kau nak orang 840 lah. Anjir.
What do you think?
Sorry, Doctor, I couldn't hear you.
Oh, you couldn't hear me. Who's talking? Anas? Is it you?
Yeah.
Okay. What do you think, Anas? If the A minus B is negative, what happened to the C flag?
If the MSB produce a carry, so carry or C will produce 1.
1, right?
Yeah. If the MSB produce a carry 1.
For the unsigned flag. For N,
Carry 1.
Alright?
Salah saya dikira.
Check how many of you is here.
Tinggi pula.
No, it's up to 49.
Pita. Ay, 50 lah.
Kemudian kau dapat lain.
Okay.
Berapa awal? 1110 tu lah. Tak, ini dia nak tengok
Want to check
ciri-ciri.
if A is less than B, we check the C flag. If
Kan
the
kau
C
dapat 10
flag
tu kan. Depan tu kau nak
is
tambah
one,
carry 1 lah.
then A is less than B. Then if N is 1 and V is 0 or either way, okay, then A is less than B.
N dengan V
If
pun benda
N
pula tu.
plus V,
N negatif, V overflow.
then and sorry, it's not plus, it's XOR. N XOR V is 1, then A is less than B. Okay, and then if we want to check if it is less or equal, we check together with Z. Okay. Z will check whether it is
Yang tu simbol buat tambah.
all the minus result really zero or not.
XOR.
The other way around is for greater than. If
XOR.
A is greater than B, then A will minus B. We will check E flag and Z flag. Then if it's greater than or equal, then we will check. This is here. Z. Or this here.
Simbol.
Doctor, your sound
Better
is
than-
very unstable.
Or equal. Okay, sorry. Now, how about now?
Yeah, it's okay now.
It's okay.
Yeah.
Is everyone
Doctor.
everyone is having problem with the sound?
Now okay.
Okay. Yeah, you
Doctor,
want to say
No,
something?
it's okay.
Can I ask about what is that the dot and circle symbol is no
Yeah, X no.
it's no X no.
The complement of XOR.
Asal dia padam or equal tu.
Okay, thank you, doctor.
Alright. Whatever it is, you will learn this more in third year.
Ada lah.
Third year in microprocessor, where you will have
Micro P.
8 flags instead of 4.
Berarti
There
kita
are
transfer ke
another
tak?
flags.
Tak.
Shit.
So for comparison, we only care about these 4 flags that is connected. The C flag, the carry, V flag is the XOR of the carry and the carry, and then Z flag is when all sum is 0, and then N flag is the S3. Okay, if S3 is 1, N is 1. If S3 is 0, N is 0. Okay. Alright. There are some mistakes in these slides, okay, that I will check later. Okay. From here, we are going to learn about multiplier. Okay. Multiplier, and your test, Okay, because someone asked during us in the group this morning. So test. So your test range is actually until next week, until chapter 6, which is the case study of the combinational logic. But
Oh, orang banyak.
if you see the test, the previous test, the 3 previous tests that I share with you, the test is basically asking about the
Itu
number
lah tu.
conversion of the sign, and then the Q format, the fixed point, floating point, and then the
Tak
marks.
tahu tu.
Hari apa
Ra-
This is what you've done previously in
Air
business
rabu-rabu.
electronics. And then the Rome,
Mana cepat jadi.
the
Rabu
principal
kelas dah penuh.
path, and then some combination of adder that you never seen before,
Power bila? Time class lah.
and probably the multiplier, but this is just an adder. Okay, this is
Arah.
added. So this is add and sub. Add and sub.
Kenapa tak buat Selasa?
And for this one, it's the same. Oh, yeah, here it has the flags, flyer, marks, multiplexer, and then
this one.
Okay.
the carry select adder, and then multiplier. So this is multiplier. This is also multiplier.
Power kan kena buka kamera.
And here is just some Boolean things, marks again,
Ya,
then
dulu kena
number
buka.
conversion, adder. Yeah. This is the latest, I think, 1920, semester 1921. So this is last year. It is done until adder. But according to the syllabus, it is until it is until chapter 6, which is the case study of combinational logic. Right. This is the course information. Okay. So we are now here doing the multiplier. So next week we are going to do the case studies on BCD adder. Not next week, this Thursday. BCD adder, incremental and comparator. So the test one will be the next week, which is on April 28th from 5 to 6 p.m. I haven't heard any complaint about this test date yet. So I think it will stick to this date
petang
and time.
pula.
Right? And the range is from
Mana mungkin.
introduction, nothing. So you don't have to worry about that. So it's from week 2 until week 7 here. Oh, sorry, it's not week 7. Combinational logic.
Ini apa? 18.
But this is just the application of the adder, subtractor, and multiplier. This is just the adder, subtractor, and multiplier application. Right? And then take notes that you have tests this week, and the next week you have to submit milestone 3. So better prepare early for that. For those who have submitted milestone 2,
Asal deadline kecil sangat.
thank you very much. And then after that, we will have semester break, and break together. Okay? They combine the break. So usually we have a semester break at week 8, but since the Eid is on week 9, so they change it to week 9, unfortunately. Right? So our break is on week 9. Alright. Okay, after week 9, I'm
Excuse
not
me.
sure.
Uh,
Question.
milestone 3, when is the submission date?
Submission date. So if week 8 is until 6 May, then it's 6 May. So week 8 Saturday, just like the previously. Milestone 2, you submit until Saturday night, right? So week 8 Saturday night, which is, if this is true, so probably 6 May. Okay. Is it? Maybe this is Thursday.
And for milestone 4, we will submit it after the Eid, so we have to
Yes,
work it
yes.
in Eid, right?
Yes.
Okay, thank you, Doctor.
Alright.
Or
Okay.
tak gila.
Back to this. Okay. So multiplier. 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 Multiplier is, okay, in all arithmetic, multiplier is quite complex compared to adder and subtractor. Multiplier is quite complex and it took a lot of resources. So what kind of resources? It's the trade-off between time delay and the area. Okay, size of the circuit means number of gates. So if you want speed, you have to deal with a lot number of gates. If you want small circuit, you have to deal with a long calculation time. Okay? You have to deal with a delay, long calculation time. So a multiplier is all about generating the partial products. So what is the partial products? Is this one. I'm sure all of you knows how to calculate multiplication, where we calculate all multiplicand. Here is called a multiplicand with bit, with every bit. Right? So it's 1101 multiply 1, 1101 multiply 1, 1101 multiply 0, 1101 multiply 1. And we also need another what we call that? Another operation, which is shifting, because we shift. Multiplier consists of add and shift. Add and shift. Okay. So first, to generate the partial product, we do the operation that is similar or equal to an operation. And then we add the partial product. First, we do the operation like AND operation. For this bit, And then when we want to multiply with another bit, we have to shift and we do the AND operation again. Then we shift when we do the AND operation between all these 4 bits and this 1 bit. Then we shift again, and then we do the AND operation between all these 4 bits and this bit. Right? It's just the normal multiplication, just like in the decimal. Right? So if we have 4-bit multiplicand, 4-bit multiplicand, where m is the number of bits, and then a q-bit multiplier, where the number of bits is q, it will generate m plus q bit product. We have m bit multiplicand and q bit multiplier. We will get m plus q bit product, and the number of partial product is equal to m or q. M or q. Is equal to q. Number of partial product is equal to q. Because we follow this one. First round, second round, third round, fourth round. Okay, this is q. So the partial product will be right. The number of partial products. Okay, this is basic. You already know the basic. Okay. But we call the multiplier, everyone knows that the multiplier is expensive. So there are intensive research on how to make multiplier less expensive, and of course one of it is to skip the 0. So to skip this stage. Whenever we find 0, we can skip that stage, but we still have to shift, do the shift and then skip this stage and then do the next stage, which is 1. That is one way, but most importantly is we want to reduce the number of partial product. We want to reduce the number of partial products so that the loop to do the error is smaller. Right? Now let's see a 2 by 2 multiplication. So this is 2 by 2 multiplication. When we do 2 by 2 multiplication with A0, A1, B0, B1, the partial product here is A0, B0, A1, B0, A0, B1, A1, B1. Know this. And before we go to the second partial product, we have to shift 1 place to the right. And the circuit will look like this for the 2 by 2 multiplier. So this term, the whole of this is called the partial product. This one is called the partial product term. Okay? So this term is calculated using AND. Okay, AND gate. For A0, B0, that will be the first bit of product. The LSB of the product. And then we shift 1 place to the right. And we have A1, B0. So that is another calculation with AND gates. And there's another 2. So we have 4 AND gates. And then when we add the partial product, see, Multiplication is about generating the partial product and adding the partial product. So when add the partial product, we can use add half adder or full adder. In this case, we only need to use half adder for both. Okay? Because both only need two input. Okay, two input. And there's no carry replay. No carry. There's one carry here. One carry here. This is carry. But there's no carry from here. So we don't need to use full adder here. You only need to use half adder here. And there is no term here. There's only carry. So we can add carry and this term. Carry and this term. Only two input, so we use half adder instead of full adder. Okay, so this is 2 by 2. Then we will see a ripple carry array multiplier. Okay. So this is an array multiplier where this is actually 4 by 4 multiplier. So how do I know this is 4 by 4 multiplier? Because I can see that there are 4 partial products. 1, 2, 3, and 4. 4 partial product and 4 bits. Okay. 1, 2, 3, 4. 4 partial product and 4 bits. So this is a 4 by 4 array multiplier. Just now, this is also an array multiplier where we have 2 by 2. Okay. Another important thing that you need to know is the adder row of adder. Row that contains adder. If we perform 2 by 2, 2 by 2 multiplication, okay, the partial product, there are 2 partial product and we need 1 row of adder, okay, to add the 2. Okay, we need between 2 partial product, we need 1 row of adder to add the 2 partial product. Okay, to add the 2 partial product, we need 1 row of adder. Okay, but if we have more, if we have 4 by 4 array multiplier, so we have 4 partial product, okay, we need 3 row of adder. 3 row of adder. Add 4 partial product. Okay. So the first partial product and the first partial product is added using 1 row, and then the sum of these 2 partial products, sum here, will become the input to the addition with the next partial product, and then the sum of that will become the input. So this is carry. The input of the next partial product, which is this one. Right? So if we have m by q array multiplier, we need q minus 1 rows of adder. Okay? Okay. Basically, we need q minus 1 rows of adder. Okay. Unless the design of the multiplier is different. Unless the design of multiplier is different where we are not using the ripple adder, ripple carry adder. We are using the other adder where we can skip a lot of addition, such as the carry save adder, for example. So if we are using carry save adder, we are adding 3, right? We are adding 3 input into 2. So we might have less than q minus 1. But here in this slide, we are talking about the ripple carry adder. Okay? So if we are using ripple carry adder, multiply the number of rows of adder needed is q minus 1 for m by q array multiplier. All right. And also still we need this number of n. Okay, so we have simplified the n gates here, but all these boxes are the results of n gates. We need n gates and then we need adder. So that's the basic multiplier using the ripple carry adder. Now we're going to see the speed multiplier. So in a ripple carry adder, a ripple carry array multiplier. Okay. The critical path, we have two critical paths. So this path and this path.
Jadi apa?
Ya,
Itu apa ni?
Agung
because
lantik
it's
si timbalan menteri tu.
ripple like this,
Dia approve.
the delay is going to be long.
Tu orang marah.
Because we need to wait
Nanti tu apa?
the lower order
Nanti timbalan
adder
menteri yang baru tu.
to produce the carry before
Yang
we
umur
can
70.
you have to wait the carry from this lower order adder before you can calculate the
Baru
next
itu cakap
bit,
kerajaan tadi duit.
the higher
Tambah
order
lagi
bit.
menteri.
Right? But if we use the save adder, if we use the carry save adder, it is less the delay is less. How do you say? Less delay. That's good. Time taken is the computation time is less computation time. It has less computation time because the carry is not ripple, but instead the carry is bring to the next adder, save as the vector, carry vector. Okay. So the waiting for the waiting in a row of adder is less waiting in the row of adder waiting for carry. So it has less computation time. and the critical path here, here, and then we have the CPA at the end, right? Carry propagation adder, or also called as vector merging adder for the carry safe adder, that merge all the partial product. Oh, sorry, the last two. The carry safe adder has 3 input, and then it will become 2. Carry safe adder will reduce 3 input to 2 input, which is the sum and the carry. And then we have to add the sum and the carry. Carry safe adder, and then we have to add the sum and the carry using the carry propagation adder. Okay, remember? So the carry propagation adder could be the carry loop ahead adder or carry ripple carry adder. So in this case, they're using the carry ripple adder. So the critical path is this path, okay, where the carry is forward to the next level, the next stage adder, and then at the last stage, since it is a propagate error, we let the carry to propagate, so the delay will go through the carry propagation. This is the path, the critical path, or carry safe adder multiplier. All right. Okay.
Share product
1 second.
generated.
My PC is stuck. Just all right. Okay. So this is a carry safe adder of the Wallace tree multiplier. So for this, I think 8-bit. 8-bit because the partial product is 8. Probably this is 8 by 8. Okay. So we have 8 partial product, and we took the partial product. Okay. And then we put it in the carry safe adder. Then we trim it down until the last adder, which is the carry propagation adder. Okay, class, can we break for 5 minutes? Because I need to do something. I need to find a figure to show you. Okay, take a rest. Right. Great. I'm back. So I just want to show you important in the test. I think the slide just want to introduce you with the Wallace tree multiplier. So what the Wallace tree multiplier did was it has the partial product generator where it will generate P0 until P7. So what is P0 until P7? So it is actually this one, the partial product. So probably this is P0, this row is P1, and so on. Oh, sorry, this is stage 0, so this must be the P0. And then this must be the P6 and P7. What they did, what the multiplier did is they took this bit, okay, it from P7, P6, and P5. Okay. They put it in the carry safe there. So P7, P6, P5, and then it will generate sum and also carry vector. Okay, so let's say this is the original. It has 3 stages of partial product to be added. These 3 stage will reduce to be 2. And what originally here now will be in this stage. Now we are taking this stage to be put in the carry safe adder. And so on. So that is what it means by this here. The partial product took the this probably 8-bit, this probably 6-bit, depending on the design. So this is just a general design of Wallace tree multiplier. Okay. But it will produce, it will make the multiplication to has less computational time, because the number of adder is less. We have 1 stage, 2 stage, 3 stage, 4 stage, and 5 stage, instead of what if it is 8, then the stage of multiplier should be 7. Okay, but now we have 6 instead of 7, and the number will be the efficiency will be much better if we have a longer bit to be added. All right. Let's moving on to the multiplication. You see this in the previous test that I showed you, okay, this morning. So you need to understand how to do multiplication with constant. So sometimes we want to multiply a number with a constant. Like this example, we want to multiply a binary number A with constant 10. So we want to multiply 10 A. And instead of, let's say A is 1001, instead of calculating this multiplication, we can just use shifter and adder. Okay, a few shifter and adder produce the multiplication product. For example, if you want to calculate 10A, okay, 10 is equal to 8 plus 2. Okay, so we can calculate 8A by shifting it 3 times to the right. And then we can calculate 2A by shifting A 1 time to the right. Okay, remember when we shift one place to the right, okay, shift one place to the right, shift A one place to the right, you will get 2A. Okay, shift A 2 place to the right, you will get 4A. Remember when we do the IEEE format, okay, we have a number, let's say 1001. If we shift one place to the right, shift one place to the right, that will be 0010. 101. Zero, 10010. We shift. Now this is like originally. Now we have 6 plus 2, that is 18. So it's like 9 times 2. Let's use a smaller number so that you will see. Let's say we have 0001. So this is 2. When we shift 1 to the right, it will be 0010. This is 2 by 2. So this is 1. This is 1. So now this is 2. And if we shift this, means the original place is here. Original place is here. If we shift it 2 times, it's 010. We'll get 1 minus 4. 1 multiplied by 4. 1 by 4. And if you shift 3 times, 1000, you get 8. So original 1. I think you understand this. So if we shift to the right, we are multiplicating it. It's 2. If we shift it to the left, we are dividing. We have 1000, that is 8. If we shift to the left, 0100, that is 4, this is 8. Divided by 2. If we shift 2 times, 0010 is 2. 8 divided by 2 and then divided again by 2. Shift 3 times. This one because 8 divided by 2 divided by 2 divided again by 2. Right? Hope you got that. So when we want to calculate back to this example, when we want to calculate 10A, we can find 8 and 2 from shifting. So we shift A 3 times, shift A 3 times to get 8A, then we shift A 1 time to get 2A, and then we add the 2 to get 10A. In other example, okay, we want to find 14A. Okay, we want to add A with a constant 14. Okay, and by 14, we can calculate 16A and then minus 2A. So we shift 16. So we shift it 4 times. We shift A 4 times to get 16A, and then we shift A 1 time to get 2A. And instead of adding, we minus the 2 to get 14A. Okay. So there could be a question like, okay, try to calculate this constant and A. Okay, try to draw the circuit. So you have to draw this circuit. Get the multiplication with constant, okay, using shifting and adding or subtracting. Right? You just need to understand the concept of shifting. Like if you shift, okay, you shift 1 place, what would it be? If you shift 2 place, what would it be? Right? First question. Which is easier to do shifting or to convert the constant to binary then multiply? It is easier to do the shifting. Okay? This is less resources. Less resources, less expensive. Because you just need to shift and then add. Okay? There's no row of adder. There's no row of adder. Alright. Okay. 10A. If A is 4-bit, if A is 4-bit, how many bit is 10A? Need to answer that? I'll go to the next or the last slide. Okay, because this is the last slide. We have about 10 minutes to go. Right? So we can also do multiplication with a lookup table. So this is the lookup table. All right. The lookup table is saved in the memory, which could be the ROM. Right? Okay. So if this is a 16 by 4 memory, so you can have 2-bit multiplicand and 2-bit multiplier, and then the product will be 4 bits. Right? Okay. And the address is this one, and this is the address of multiplier. And this is the address of multiplicand. Address of y and address of x. Okay. Now inside here, ooh, is the product. Let's say you want to calculate 0, 1, 0, 1. Okay, sorry, this is only 2 bit. You want to calculate multiplicand 0, 1 with multiplier 1, 1. So you just check the address of multiplicand 0, 1, and then the address of multiplier 1, 1, and then you can find the answer. Is here. Okay, this is the answer. It's here. You have to find the grid of 0, 1 and 1, 1, which is 0, 0, 1, 1. Right? So that is how you use the lookup table. Okay? But lookup table, if the bits of the multiplicand and multiplier is bigger, it will take more space. Take a lot of space, of memory space. It will be faster because we just have to search for the address and then look for the answer, but it will take a lot of memory space, right? So that is all about the multiplier. Let's go back to the questions that are left with you. Okay. If A is 4 bit, how many bit is 10A? Okay. Remember, okay, if M bit might multiply N bit, you will get M plus N bit. Okay. 10, how many bit is 10? Okay, 10 is
4 bit.
okay, 10 is 4 bit, right? Because it's 1010. Okay. This is 10. 10 is 4 bit. A is 4 bit. Okay. Now, how many bit is 10A? 10A is 4 plus 4.
8 bit.
8 bits, right? 8 bits. Okay. I asked you that because that was in the questions that I saw. Here. How many bits are there in Y? How many bits are Y? Which is 12x. Okay. Just for you to know that how to answer that. Okay. 12 is one number, x is another number, x is 4 bit. Okay. 12 is another bit. 12 is another number. Okay. And you get Y as 8 bit here because 12 is also 4 bits. Okay. Represent in 4 bits. At least, right? So the answer is 8 bit. All right. That's all for today. So I wanted to do this together, but seems like we don't have the time to do it together. Maybe you can do it first, and if you have questions, then I will check the answer for you. And I will upload the answer for the exercise that you have done previously. So that will be your study before the test for chapter 2 until chapter 4 because this is chapter 5, right? So for chapter 5 exercise, you can try to do all the multiplications and addition and maybe subtraction in these three past year questions that I share with you. Right? especially this one. I have done this one, but I'm not sure if I get the correct answer. I need to check with other lecturer if I got the correct answer or not. All right, so that's all for today. Oh, for those who are buying the CPLD, you can get the CPLD today or tomorrow if you have time. I think I'll be in the lab. Okay, it's VCAT lab P04, the first floor. Find the glass door. Okay, you will find me from there, or you text me whenever you want to come, and I'll wait for you. Okay, I'll wait for you in the lab. Okay, so someone's asking, can I provide the answer for this for the test? Honestly, I don't have the answer. So I only know the answer when I try to do it, but I don't know if that's the correct answer. And I will not only provide you the answer, you have to give me your answer first, then I will check if that's correct or not. Okay. So I think that's all about the announcement. Okay. The test is until the next chapter, which is chapter 6. But as you can see from the previous test, it is basically until the multiplier. Okay, multiplier. But even though it is a multiplier, it is basically an adder. Okay, using adder as a multiplier and so on. And that is for tests. And for those who are buying CPLD, I will be in the lab this afternoon. You can come and get it from me. Text me first before you come. And is that all? Yeah, for this exercise for multiplier, you can try to answer the questions from the 3 previous tests that I gave you, and I will check your answer. Okay, I will check your answer. Okay, so that is all from me. See you Thursday, same time, 8:15. Right? If I don't announce in the group the night before, it will be 8:15. 8:15 on Thursday. All right, so that's all for chapter 5, and that's all for today. Okay, see you Thursday. If there's no more questions.
Thank you, Doctor.
Questions? Oh, thank you. You're welcome.
Thank you. Yeah, thank you.
Okay, you're welcome.
Doctor, yeah, I have like a small question.
Yeah, small questions.
For our calculator, what carry or what for others they are using to make it faster, if you know.
For our computer
Calculators.
calculator,
Yeah.
I don't know what. Like,
You know,
is
like
it
this is
like?
like a random question. It's okay if you don't know.
Oh, I'm not sure if it's the analog calculator, the circuit in the calculator, but if it's in your phone, if you are using iPhone, I think it depends on the processor, which is iPhone has its own processor, right? Like on Android has the Qualcomm Snapdragon, Apple has the A4, A9, now it's A11, and they are doing a business. So basically, they will not tell what kind of uh, multiplier or adder that they are using because that's business. If you are
Oh,
looking for um, open source like RISC-V, okay, RISC-V is open source where you can design your own adder and put it in the RISC-V. Okay. Also, I'm not sure which adder is used in the RISC-V by default, but the as far as I know, the most fastest adder is called the Brancung adder. Okay, that's the last time I checked. But I think there will be like trade-off of this and that. But so the adder is it's a trade-off between area and speed, right? So if you want area, it is better to use adder like using the ripple carry adder or the carry safe adder, like the Brancung, the Wallace tree. So that's the fastest adder. Okay, but
yeah, the fastest
among
one
all,
is CSA, right?
yeah, the
Carry
carry
save
safe adder. The Wallace tree
Yeah.
is the carry safe adder. the Brankung adder is also the carry safe adder, and there if you want faster than that, you have to design it at the transistor level. So if the transistor itself is fast, then the adder will be much faster. Right now, they are trying to make faster adder by designing at the transistor level, but I'm not doing research at the transistor level, so I don't really interested in doing the finding the fastest adder anymore. Okay, I will stick at the Brankung adder. This is the fastest adder that I know. All right.
Yeah,
Thank
okay.
you for the questions, Anas.
Yeah.
All right. So it's 10 a.m. Have a nice week, everyone. Hopefully your week will be fine until Thursday. Okay. No more hardship until Thursday. Okay. So see you on Thursday, 8:15.
Yeah, okay. So I'm sorry, doctor, for lagging today,
Yes.
but my connection is not stable.
Oh, okay. Don't worry about it, Anas. It's okay.
Okay.
We're fine. We finished the chapter. All right. Thanks, everyone. I'm going to
Doctor, can I have the
Yes.
attendance again, please?
Sorry again.
Can I have the attendance again, please?
Attendance.
Yes.
Oh, attendance. I will check the report from the
Ada attendance ah?
Oh, okay.
So if you are in now, of course you are in
Budak
now.
international pelik-pelik.
The report from what again, Doctor, please?
Uish. Aku dah keluar dah sikit.
Tiba-tiba minta attendance.